Week 6 in OSH 200. Here in Week 6, we're going to be discussing some additional tools that a safety professional would have at their disposal to help identify and verify potential measures. But they can also be used to gauge performance of safety initiatives as they relate to business value beyond mere injury prevention. We're particularly going to discuss probability and some financial metrics. Keep in mind that Week 6 lecture is a brief fundamental survey of just a few probability and financial metrics tools that can be used. Students and safety professionals should dig deeper, expand their knowledge of these topics as they are extremely important in the ongoing management of occupational safety. So without further ado, let's go ahead and get into talking first about probability. Let's first define probability. At its core, we're trying to describe the likelihood of an event occurring, or maybe it's a series of events occurring. It can be expressed qualitatively, such as it's very likely, unlikely, impossible, or other terms that are just words and frequently seen in risk assessment. Or it can be expressed quantitatively, meaning we're going to put some numbers to it to describe the probability. In this course, we're going to focus on the quantitative expressions, and particularly in this week. As you can tell, when we utilize the words likelihood and qualitatively and quantitatively, it should spur some flashbacks of risk assessment, because this is where probability is most useful, is when we're utilizing risk assessment. And if you recall from Week 4, we discussed that assessing risk and doing risk assessment is part of the first 3 steps, particularly when we're trying to identify low frequency yet very high severity risk. We're wanting to put a number, a quantity on the likelihood of those events. Looking at probability, looking at components in systems, many times hardware, it's extremely helpful for us to quantitatively express probability. Keep in mind that probability, as we're going to express it here, is again merely a ratio of 0 to 1. You might also think of it as a percent, meaning 0% means the event would be impossible. It's not going to occur, as a matter of fact. 100% likely, meaning it will happen without a doubt. And obviously, everything lies within the range of 0 to 1. Exceeding 1 is a problem. So if we ever get to that point, you know there's something wrong if your ratio or your probability comes up greater than 1. There's various types of probability. These are just 3 common types that we see calculated. It's the 3 we're going to focus on in Week 6. But keep in mind that there's Poisson distributions and other tools that you should look at and can look at later on. We're going to focus on these 3 simple ones as part of a 200-level course on safety metrics. When you're calculating the probability, quantitatively expressing it, keep in mind that when you're doing the calculations, you have to understand the context or the background or the setup, if you will, of the events. Particularly knowing if we're talking about multiple events and we're using the word and or the word or, because they create or they prompt you to use 2 different operators. You're going to see that when you see the word and, or it's a situation where we're looking at this event and another event occurring, we're going to multiply. And then when we see the probability or we see the word or, we know we're going to add, because the probability of one thing or the other occurring is more likely than having 2 events both occur at the same time. But we'll get there later. The application in safety measurement, I really want to hammer this home, as it's important as we go forward for you to understand why this is important and why we're discussing this. The most useful aspect in safety measurement for probability is in assessing risk. We can identify and prioritize leading metrics. Again, I refer you back to the Week 4 lecture, when we calculate probability and put a quantity to the likelihood of an event occurring. And it is also helpful in calculating how much risk we have reduced. And ultimately, or arguably, it's the ultimate safety performance is us reducing risk. And when we can put a number to it, maybe we've instituted a safety control, a new method, a new process, maybe it's a new piece of equipment that lowers the probability of an event occurring, we have, in effect, reduced risk, which represents safety performance. So I hope you really understand the application and the reason we're talking about probability in this class. So let's dive in and talk about simple, joint, and compound probability, how we calculate it, what it means, and how it applies to safety, and some hypothetical examples. First of all, in calculating simple probability, it's expressed as the function of A or probability of A. We're just using A here as a variable, as a placeholder. And if we're calculating the simple probability of a single event, we look at those number of events that could occur that meet our criteria, the A events, if you will, versus the total number of all possible events. Now, at the heart, that is the formula for simple probability. It's very simple. How many A's could we have versus all possible events? It might be helpful if I were to give you a very common example, a common application in everyday life, or at least common life, or a term that folks are commonly aware of. And let's think about dice, whether you're playing Monopoly or maybe you're at a casino. Most folks are familiar with dice, and obviously the singular term would be die. Let's say we wanted to determine the odds of rolling a 3 with the single roll of a single die. We only have one die. We don't have a pair of dice. We're just going to roll that one die. What are the odds that it will land on a 3? So P of A means 3 in this case. What's the probability of rolling a 3? Well, there's only one 3 on a single die. However, there are 6 possibilities. There are 6 numbers on a normal die. There's only one 3, meaning 1 out of 6 is the probability of rolling a 3. If we divide 1 into 6, we see that's 0.167, or 16.7% chance of rolling a 3 if we have a single die on a single roll. Let me show you that a little bit differently. If we were to count this up, we would know here are the sides of a normal individual die. One side has a 1, another side has a 2, another side has a 3, and so on and so forth. Our P of A, the event we're looking for, is just a 3. So that's the only event that will satisfy what we're evaluating as a 3. We're not asking what are the odds of rolling a 3 or a 2 or a 3 or a 4, or the odds of rolling a 5, or the odds of rolling an even number. We're asking just a 3. What are the odds of rolling a 3? Well, they're 1 in 6. There are 6 possibilities, as you see here, but there's only one that satisfies the criteria. It's a 3. So it's a 1 in 6. Let's apply that in a safety context. Commonly in some textbooks, you'll see probability, simple probability, discussed in terms of injuries. So we'll present one here as well. Let's presume that there are 135 eye injuries for a particular facility between 2015 and 2017. Now, if that's a small facility, that's a lot of eye injuries, but we'll just utilize it here for illustration purposes. Let's say we examine those, and 53 of those 135 eye injuries are related to employees not wearing eye protection. Let's say we want to know, what is the probability of one of our eye injuries being related to not wearing safety glasses at present time? So our P of A is knowing what's the probability of an eye injury related to not wearing safety glasses. Well, we had 53 such events out of 135 total events. So 53 divided by 135 is 0.39, or 39%. Now, I'm not sure what utility or the extent to this is useful in saying, well, there's a 53% chance that our eye injuries will not be or will be related to people not wearing safety glasses. That's pretty evident in just doing a very simple percentage calculation. I'm not sure what its forward projection utility is for us. But let's say we're wanting to quantify risk associated with something. We want to see what is the likelihood. And let's say we're going to look at the probability of a safety device failure. And here we want to solve for the probability the machine guard malfunctions. Say we have test data. Maybe it's from a manufacturer, or we are the manufacturer of the safety device that's used in machine guard. And let's say we cycled it 12,000 times. And during those 12,000 times, we had 23 failures of the machine guard device. So 23 divided by 12,000 equals 0.0019. And you'll notice that there's a typo here. It should be, no, excuse me, it's not a typo. It is 0.19%. So if you were tempted to think it was a typo, it's not. It is actually a percentage of a percentage. It is 0.19%. We move the decimal place two spots to the right. We'll see it's a 0.19% chance that this machine guard will fail. So our P of A here, we're solving for the probability it'll fail. We've had 23 failures. Those are the type of events versus all the opportunities for the event, which were 12,000. So I hope you see the application here of a simple probability. Let's go on to a joint probability. Here we're determining the probability when there are two events occurring. We're interested in knowing, well, what's the probability of both event A and B occurring? So here we got to see that we have to have the stars aligned just right. Both A and B have to occur. Well, the probability of two things happening at the same time is usually, will be less than either or occurring. And we're going to get there. But joint probability, let's again look at it in a common everyday term with die and dice. Suppose the probability of A and B is the odds of rolling a 1 with the single roll of two dice. So we're solving what are the odds basically of rolling snake eyes. Both die land on 1 with a single toss of both die at the same time. So P of A is the probability of rolling 1 with the first die, which is 1 in 6. And we also have to look at the probability of rolling a 1 with the second die, which is also 1 in 6. There's only 1 1 on the first die and only 1 1 on the second die, and there are a total of 6 sides on both. So we're looking at having to have one land on the 1 and the other one. In this case, we would multiply. 1 in 6 multiplied by 1 in 6 is 0.028. We move the decimal point. Well, notice this is a 2.8% chance that we'll have snake eyes. So here's a point for thought. When you encounter an and situation, you need to think multiply, because the odds of two events happening together are less than just one or the other. And it makes sense. So if you multiply fractions or decimals, the product of that multiplication exercise is always a smaller number. So let's look at it from an or standpoint. And we'll still put this in the term of joint probability, although some things you might read might start getting into the world of compound probability, which we're going to go there next. But since we're dealing with two die, we basically have mutually exclusive things. If one's going to land on one thing and the other one's going to land on the other, and we're doing it at the same time, maybe this time instead of wanting to know what are the odds of rolling snake eyes, we want to know what are the odds of rolling a 1 with either die, meaning one can land on a 1 and the other one can land on any of the 6 numbers in a single roll of 2 dice. In other words, what are the odds of one of the 2 die will land on a 1? The probability of rolling a 1 with the first die is 1 in 6, and the probability of rolling a 1 with the second die is 1 in 6. But we're not interested in calculating and, although those are both the individual probabilities. We want to know what is it that one of them will land. Well, it's 1 in 6 or 1 in 6. Either die landing on 1 satisfies the requirement. When we have an or, we're going to add. So here, 1 6 plus 1 6 is 2 6 or 1/3. So that's 33 1/3% chance that one of the die will land on a 1 on a single roll of 2 dice. Another point for thought, when you encounter an or situation, think add. Keep in mind the odds of just one of 2 events happening is greater than both happening together. So if you add fractions or decimals, the sum of that addition calculation is always going to result in a larger number. So that's something you can keep in mind. The odds of either or thing happening are going to be greater than both. Therefore, it's going to be a higher number. And I'm dealing with fractions with probability always, and dealing with decimals always. To get a higher number, I'm going to have to add these things together. So let's talk about this in a safety application situation. And what's the probability of a double machine guard failure? Suppose employees are protected from entering a large turret press path of operation by an area lock curtain. Further, suppose that as a backup, there's a pressure mats on the floor that shut the turret press down should an employee enter the path while the press is in operation. The probability of the lock curtain failing is 0.0003. Probability pressure mat failing may be 0.0002. So the first one will be 3 in 10,000, and the other one is 2 in 10,000. Here we're looking at what are the odds that both of these things would fail at the same time. So it's a multiplication exercise. Remember, that's an and. What is the probability of the lock curtain failing and the pressure mat failing at the same time? 0.003 multiplied by 0.002 equals, and you'll see there's a lot of zeros leading up to that, 7 as a matter of fact. You'll count 7 leading zeros. If we were to move that decimal point all the way to the right of that 6, you would see that we moved it 8 places. That's why if we were to express it more in scientific notation, it would be 6 times 10 to the negative 8. So you see that having a backup, or we have a redundancy here, greatly reduces the odds of a negative event or an injury or a loss event. Let's shift gears here and let's talk about compound probability. Here we're determining probability of 2 independent events occurring. The key question we think about when we have these independent events, and we're talking about from this or perspective here, is are they mutually exclusive? Meaning, can it only be one or the other, that both events cannot happen at the same time together? If they can't happen at the same time, they're considered mutually exclusive. However, if both could occur at the same time, we treat them as just being independent. There's really 2 ways we look at this from a formula perspective. If they're mutually exclusive, meaning the probability of A or B, and we're calculating the probability of either event A or event B occurring, we're going to add the 2 probabilities together. Since there's no chance that both of them could happen at the same time, that's all we need to do. However, if they were not mutually exclusive, meaning they could both occur at the same time, we would calculate and add the probabilities of A and B, but subtract that from the probabilities of both of them happening at the same time. We do this in order to avoid double counting the probabilities, because there's going to be overlap here. The same formula could be applied even in a mutually exclusive. So the bottom formula could be applied to the top. But since both A and B cannot happen at the same time, we recall that when we have a situation like that, that is a 0 on the ratio scale. PA plus PB minus 0 will equal the same thing. So it's just omitted in the first or the top formula you see there for mutually exclusive events. Let's apply this in a setting that we might see in evaluating risk or doing risk assessment, particularly in a process safety management or chemical type industry. We're going to start with just a common everyday example and then work our way up into maybe something a little more complicated, certainly on the assignment. Let's do a fault tree analysis. A fault tree analysis is a tool used in system safety, is a tool we use to evaluate risk. It's a tool that we look at a system, and usually we're talking about components, a hardware system. Maybe it is a chemical reactor, maybe it is a piece of equipment, and we're looking at all the components. With fault tree, we start with a negative event. What's the negative outcome that we're wanting to analyze and figure out how could it possibly occur by looking at all the components in the system? Now, there's a counterpart to this called failure modes and effects analysis. There we start with the components, put them in failure mode, or say, okay, here's how they could fail, and then we figure out what negative events could occur as a result of their failure. Fault tree analysis simply starts with the failure and works its way back the other way. So let's say here, this is in a diagram of a flashlight. We're going to use a flashlight as an example. Now, you'll see here that there's somewhat electrical schematic icons and diagrams being used here. At the top, we'll see that there's a switch. This represents a switch. Over here on the right, looks like the sun. That's representing the bulb of a flashlight. The lines that are going around represents the wires. I suppose most simple flashlights don't have a capacitor, but I threw one in here anyway. I'm not sure why they'd have it, but we'll go with it. Follow the wire around, and you'll see here these are the batteries or cells, power cells, because this will be a DC circuit or DC powered flashlight. And we have batteries here, when we think about that, that are in what we call series, meaning they touch one another. And the current flows in this direction. So we have a switch, we have a bulb, we have a capacitor, we have the wire, and we have two cells. If we were going to put this into a fault tree, it would look something like this. Now, please keep in mind that there actually is a systematic means to go about constructing a fault tree. That rectangles, circles, and the various shapes of gates, those things have specific meanings. There's a specific order to this. Purpose of this class and this week is not to teach those, but do keep that in mind that they exist. Let's say that the negative event we're starting with here is having no light. Now, where I come from in southeastern Kentucky, we would say the flashlight won't burn. But I've had folks point out to me that that's probably not accurate because we're not talking about this flashlight combusting. We're talking about it not working, or in other words, not producing light. So that's the negative event we start with. And then we look at the components and how could they fail here. In the middle, you'll see something, this curved shape that's pointing upward here. We would call this, these are gates, meaning how these events relate to the negative event, top event that we've defined first. When you see it curved up like this, it represents what we call an OR gate, meaning that the bulb or the wiring or the switch or the second battery or first battery or the capacitor, if any of these components malfunction, we will arrive at having no light. So it's capacitor or the first battery or the second battery or the switch or the wiring or the bulb. Hence we use an OR gate. It only takes one of these failures to produce the negative event. So let's say we were able to get some failure rates on these components. Maybe the manufacturer puts them out. Maybe a lab has tested these components. I seriously doubt that you're going to find this kind of information for a simple, cheap flashlight. But if we were talking about components in a chemical reactor, we'd probably be able to find this kind of data. And that's where the application would usually be, safety. But let's say the failure rate for the bulb is 0.001, meaning 1 in 1,000. The wiring failure rate's 1 in 10,000. The capacitor failure rate's 2 in every 1,000. Switch failure rate being 3 in every 1,000. And then each battery has the same failure rate of 4 in 1,000. Since it is an OR situation, meaning the bulb or the wiring or the capacitor or the switch or either of the batteries failing, we add those probabilities together and we see that the probability of having no light based on these failure rates is 1.4%, meaning that 1.4 times out of 100, we can expect our flashlight to fail. Now, let's say we change this and we now wire the flashlight up in what we call parallel. If you know anything about electricity or these kind of schematics, you know that here we could still have light if one of the batteries fails. Now, it might not be as bright, but we're not going to have no light. We're not going to have the negative event because of one battery failing. So we still have the switch and the bulb and the capacitor and the wiring. We've just changed how we wire up the batteries. What does that do to our fault tree? Well, when we do it, when we make that one change, you'll see we still have our negative event at the top. We still have this OR gate, but we change things here. Now, it's a capacitor malfunction, or we have to have both battery 1 and battery 2 fail. Here you'll see, and I put it in red, an AND gate. So now it's battery 1 and battery 2 both have to fail in order for this battery or cell malfunction to occur. Didn't change anything with the switch, wiring, or bulb. How does that impact the quantitative probability of failure here? Well, let's take a look at it. Everything's the same, except if we go down to the calculation, we see we're adding the bulb failure rate to the wiring failure rate to the capacitor to the switch, and we're still adding. But notice what we did with the two failure rates here. We have to have both battery 1 and, hence the multiplication, battery 2 fail at the same time. So 0.1 or 1 in 1,000, 1 in 10,000, 2 in 1,000, 3 in 1,000 plus these two quantities goes to a 0.006. Now we went from having a 1.4 chances out of 100 of our flashlight not working to 6 in 1,000 chances. We reduced it drastically simply by making a change, or in essence, we did a redundancy. So I hope you see how probability can play into things. If this were not a flashlight and maybe we're adding a backup relief valve, or maybe we're adding a backup machine guard, you see how it reduces the likelihood component of a risk assessment calculation. So that's probability in a nutshell, and the extent of which we're going to dive into it in this OSH 200 course. As mentioned, I encourage you to dive deeper, explore probability and how it plays in. But because this course looks at safety measurement as a whole, we've got to move on, and we're going to talk about something else. Again, another tool in the toolbox. Not always itself a measure, but it tells us about other measures. And that's dealing with some financial metrics. And specifically, we're going to discuss two. One is return on investment, or ROI, and the other one deals with the time value of money, TMV. Now, I can tell you both of these are calculations that are part of the CSP exam, things you would have to prep for and know something about as you prepare for that exam later on in your career to get the professional certification. So let's talk about these two individually. First, we're going to talk about return on investment, then we'll talk about time value of money. But first, let's make sure you understand why we're talking about this and knowing why it's important. First and foremost, financial metrics is the language of business. Now, just because we speak in terms of dollars and cents does not always mean that there's something unethical or something wrong. Ultimately, safety professionals are hired to protect life, first and foremost, and the wellness of people. That's our job. That's our creed as occupational safety professionals. But organizations also hire us to save them money. And whether it be a nonprofit or for-profit, understanding money and financial metrics is a language that senior leadership understands. They understand immediately how it impacts the overall sustainability of the organization, and we need to know how to speak that language, at least to a certain extent. It also helps us establish credibility. When we can show there's a return on investment, or something makes financial sense in addition to preventing injuries, and usually it's not in addition, they go hand in hand, it establishes credibility. We can also show the return, the financial return, in addition to merely preventing injuries, then we see build credibility in ourselves. And the third bullet goes hand in hand with the credibility. It helps us secure support when we are trying to get approval for a safety initiative or a capital expenditure in safety. We have to many times show what it means from a business standpoint, and to get the support and to get the green light, to get the approval on a large project. Many times we have to also discuss the finances. And bullet 4 really is something that I tell safety professionals many times in safety departments and organizations, that we should seek first to reduce injuries, because that's what we do. That's our creed, is to protect the life and well-being of people. But when our systems and our initiatives start showing value to the organization enterprise-wide, meaning we also improve productivity, or we improve quality, we start seeing return on investment that go beyond just preventing injuries, we start to see a lot more value in what we bring to the organization. So we measure the value of our safety performance, or possibly it's just we've reduced injuries, and that in itself is value to the enterprise. So let's first talk about return on investment. What is it? Again, we're talking about a ratio, and it's the ratio of benefit to cost at its core. It is a ratio, a rate of benefit to cost. It's a metric of profitability for an investment, and it's a very simple one. And we look at profitability gain compared to the cost. Now, ROI is expressed different ways. Depends on what context you're looking at it or what source. On the left, you'll see ROI expressed as profit in dollars versus cost. Usually looked at purely when we're looking at our goods and services that we produce versus what it costs us to do. We see a return on investment. But that can also get into just talking about revenue. Now, if we go over to the investment world and you read folks who deal with personal finances and financial planners, they'll talk about it in terms of the formula on the right. Investment gain in dollars minus the investment cost in dollars divided by the investment cost. Keep in mind here, the term investment gain is more about a sales price of an investment minus what we paid for it. That would be the investment cost. So if I bought stocks at $50 a share, that would be my cost. And then if I sell them at $75 a share, that means I had $25 in the numerator divided by my initial cost of $50. And that is an ROI of 0.5. It is a return, but is it a rate that we really want? But again, the formula on the right is what we see normally when we're talking about investments. We're looking at the sale price of the investment versus what we paid for the investment. In safety, however, as you'll see, I've put it in a box. I've said, here's our focus, the formula we're looking at. Many times we're looking at what are we saving in loss? Because safety, we help maximize the production of goods or the production of services. But we don't actually produce goods or services. We save cost to the organization. So it's the savings divided by the investment cost. It's a simple formula. It's probably the most straightforward. And it's the one we're focusing on here in OSH 200. So when we talk about return on investment, it's going to be a ratio. And we're going to talk about savings. Dollars to investment cost in dollars. So let's look at a return on investment safety example. Now I've got quite a bit of background information here. I want you to listen and I want you to think about the whole scenario. Then we're going to break it down. This scenario is going to be much more detailed and much more in-depth than what you're going to see on the assignment that accompanies this. So if you understand and follow along with this, the assignment, the question that accompanies this week will seem rather simple to you. So over the last 3 years, Widget Co. has averaged 20 eye injuries that involve foreign bodies in the eye. So 20 eye injuries that involve foreign bodies in the eye. That means they could have had other eye injuries that just weren't foreign bodies in the eye. They could have lacerations, cuts. But we're just looking at the foreign body in the eye. And on average, of these 20 foreign bodies, 16 are attributed to employees not wearing safety glasses. Now, suppose you do an investigation that reveals that at least 50% of the employees involved in the 16 foreign body eye injuries, those that involve not wearing safety glasses, attribute non-compliance to safety glasses being uncomfortable. They just don't like wearing these cheap glasses. They hurt their temple, they hurt their nose, they fog up. Who knows what the reason is, but 50% of the employees involved in these 16 attributed their non-compliance. The reason they didn't wear it is because the safety glasses are just too uncomfortable. You set out to solve this problem. You locate some new, more comfortable safety glasses. The supplier, the manufacturer of the safety equipment, they give you samples. And after you give them to a group of employees that are representative of the population of non-compliance, you want to make sure that you're giving these folks to the same group, the same area, groups of the plant, the population that involved the 16 that we mentioned earlier. And you determine that with the new safety glasses, you improve compliance by 50% of what it is now with these new safety glasses. So let's presume that Widget Co.'s average workers' comp cost per foreign body eye injury, $645. So for each eye injury, That involves a foreign body in the eye, $645. Current safety glasses cost Widget Co. $3.12 for each pair. And on average, each employee is going through 3 pairs of safety glasses per year. There's 200 employees that are required to wear the aforementioned or the safety glasses we just talked about. The new safety glasses are quite a bit more expensive, as you can tell. They're $8.45 a pair, and it appears employees are still going to use 3 of those per year, kind of keeping it simple. So let's ask this question. Is there a return on investment to support these new, much more expensive safety glasses? Is there a return on investment to support the safety glasses switch? Well, let's first say, what's the cost of this investment? Let's look at that first. Right now, we're paying $3.12 per pair for 200 employees at 3 pair per year. So that means, on average, here, we're spending $1,872 per year on safety glasses. The investment, however, we're going to be spending $5,070 a year on safety glasses. Now, to figure out what that's going to cost us over the course of 3 years, because remember, our data that we looked at, and I'll go back there, is over the last 3 years. So 3 years is the kind of what we're working off of. We would have to look at what's that investment cost a year. Remember, we're spending $1,872 anyway, so we would subtract that from the new cost of safety glasses, meaning the investment cost per year is $3,198. We multiply that by 3 years. We see that over 3 years, this investment cost is $9,594. Our next step will be, what are the savings? We've got our denominator. Let's look at the numerator. Well, our eye injuries that involve the foreign bodies in the eye are $645 per. And remember, we had said 16 of those are from not wearing safety glasses. So about $10,320 a year for those injuries where they're not wearing safety glasses. So if we say we're going to cut out half of those, that means we reduce the cost by $5,160, or that is actually what it will cost now. That's going to be, it also represents a saving. We're splitting it down the middle. So remember, the new glasses reduce compliance by 50%. So if that is what represents in savings per year, we multiply that by 3 years, that means we're going to save $15,480 over 3 years with the new glasses. So what's the ROI? Well, $15,480 divided by $9,594 equals 1.6. But what does that mean? In everyday terms, that means for every dollar spent on the new glasses, Widget Co. will save $1.60 in eye injury costs. And keep in mind, this is just the direct cost. We haven't discussed the iceberg theory in this class, where direct costs are the things that are at the top of the iceberg that we see. They're floating around. There are things that we can usually put an exact dollar figure for, such as medical bills, lost time away from work. The things underneath, the indirect cost, are those things such as morale and overtime and customer relations that's sometimes hard to put a precise figure on. We're just talking about direct cost here, that for every dollar we spend on the new glasses, we save $1.60 in eye injury costs. So the question, does the return on investment support the switch? That is an emphatic yes. It's a tremendous savings for the company. Even though it's costing them more in safety glasses, they're going to save money. Switch gears and talk about the time value of money. Why does it matter? Well, many times we need to understand what's the long-term impact of a safety investment. Management and executives within an organization, they think like this. We need to be able to at least speak the language in fundamental terms. And we want to also properly evaluate the investments in safety. And here's what we got to understand, is that there's this concept of compounding interest and earning in investments. Time value of money is a tremendous thing for us to understand, not just in safety, but in our personal lives as we plan for retirement and other things. The power of compounding interest is incredible, and we really need to consider that when we're talking about money we're going to spend on a safety investment. Now, there's that we could dive really deep in time value of money, but we're going to look at 2 of the fundamental equations that you would see on the CSP exam that you're preparing for later on in your career. We're going to calculate the future value of a present sum, but we could also look at the present value of a future sum by just manipulating the formula. For this class, we're going to focus our attention here on the formula on the left. I'm going to go ahead and give you a hint. This is what you're going to utilize in the assignment that accompanies this. And the key to the formula is here, or the variables in the formula. FV equals future value. Many times that's what we're solving for. Present value means how much is the investment we're going to have to make right now. I would be interest rate, that is the percentage, and N means number of periods. Now, normally we're talking about years here in the N. However, the N could be months. We just need to make sure that the interest rate corresponds. If we're going to count months for N, our interest rate is compounding on a monthly basis as well. I'm not going to throw a curveball like that at you. However, we can also calculate the present value of a future sum. Maybe we're going to earn this later. We're going to save this later. What's that value to us now? All we do is simply, as you can see, manipulate the formula doing some really basic algebra. If we divide both sides by the quantity 1 plus I to the nth power, we will see PV equals FV divided by 1 plus I, that quantity raised to the n. So let's apply this to safety. Suppose we have a safety intervention and it's going to save us $48,000 a year. What's the value of $48,000 in 5 years from now? Assuming we're not investing this, we're just talking about inflation occurring at 2.5%. Now, if you look at the past years, inflation has fluctuated, and it's usually been less than 2% over the last 3 or 4 years, but we'll go ahead and call it 2.5%. Let's assume inflation is going to be that for the next 5 years. If we plug this into our formula, $48,000 is the present sum, and we're going to multiply that 1 plus 0.025. That is 2.5%, right? We raise it to the 5th power because it's 5 years. We would find the future value of this present sum, $48,000 today, will be worth $54,308 in 5 years based on just this inflation. Now, there's a supplemental video that's showing you how to use a calculator, specifically the Texas Instruments TI-30X 2S. You can utilize Microsoft Excel. There are also online calculators that calculate this for you. I would encourage you to check those out. You can actually utilize this example, plug it in to make sure the one you found online will actually come up with a correct response. So I hope this helps you in understanding how probability, some financial metrics are additional tools in the safety professional's toolbox that help us, one, identify and evaluate the measures we've selected, or tell us, as our safety investments produce making business sense as well. If you have any questions, don't hesitate to ask. Thank you.